All right, welcome to another warm-up. Take a few minutes, give these three a try. They're almost all, actually no, they are all just practice and review from last time. So hopefully they go nice and smooth. Okay, if you're listening to me now, you should have already tried these, at least gone so far to the point where you got stuck independently on all of them. Let's go ahead and work through them. I'm going to give myself a bit of space here. Let's do this one slow and then we'll do it fast. So our limit laws say the following. It says I can split up this limit into a bunch of different things. It says I can, each of those plus signs, I can take those limits individually. And I'm going to go ahead and edit this in a second too. So I can look at those all on their own. Further, they say I can go ahead and take this 5 and I can pull it outside of my limit. They say I can take this 2 this and pull it out. And I can take that 4 and pull it out. And then they also tell me that the limit as x goes to 2 of 64 is just 64. That x64 doesn't really care what x is. Okay, finally they tell me that the limit as x goes to 2 of x is just 2. If x is going to 2, then what happens as x goes to 2? It goes to 2. So this becomes 2 to the 5th plus 2 times 2 to the 4th minus 64 equals, if I did this right, 0. That's 32 plus 32 minus 64 is 0. All right, that was the really slow way. That's a super true way. But we also said, hey, as we get more comfortable with this, we can take a few more liberties. And especially because this is a polynomial, we know that we can get a polynomial just by plugging in. That a polynomial, the word is continuous, that we're allowed to just plug in this 2 here into a polynomial. But let's go somewhere in the middle. I know I can break up across these plus and minus signs, and so what I'll often do is I'll just kind of use these arrows and I'll say, okay, 2 to the 5th is 32, 2 times x to the 4th is 32, and then 64 is just 64. So this is 32 plus 32 minus 64. Okay, so I really do need you to write limits when we have limits. You don't get to drop this thing, but a little bit of saying, hey, let's just take an arrow to evaluate what happens here and here and here is also gonna, it's pretty common. A lot of people do this, and especially for something like a polynomial or a rational function, you'll see this a lot. And this again is 0. So this is the full expansion, but I'll be doing a lot of arrows along the way to a little bit of a negotiation between having to write this limit thing out all the time. Great, hopefully that went well. Number 2, looks a whole heck of a lot like a warm-up from last time. Let's try this again. This is something called our difference quotient. We'll be seeing it a lot. What this is really saying is that what this is going to give us is the slope of our tangent line when x equals 3 for the function y equals x squared. So getting a little bit ahead, but something very much like this is going to give us the slope of our tangent line. But for right now, let's just see if we can work this out. If we try to plug in here, we get 0 over 0. And that doesn't equal 0, it doesn't equal 1. It just means we have to do more work. And usually that work for something like 0 over 0 is going to mean that we are going to simplify like crazy. So let's simplify like crazy. This is going to equal the limit as h goes to 0 of, expand this whole top out, I get 9 plus 6h plus h squared minus that 9 all over h. That's great. It looks like I get to cancel out those 9s. What I'm left with is a bunch of h's that I should be able to cancel. I'm going to do it in 2 lines. Maybe you could do it in 1. If I pull out that h out front, I would get, looks like 6 plus h all over h times 1. And I get this limit as h goes to 0 of 6 plus h over 1. Okay, notice that we just canceled out these x's here. Sorry, these h's here. And before, when we did that, we would have to say, okay, that's true as long as h is not 0. Then we're allowed to cancel this. But in the limit, the one place the limit does not look and cannot look is at this 0. It's not allowed to look at where it's going. It's only allowed to look nearby. And so we don't need to worry about that when h is not equal to 0. That limit takes care of that for us. Okay, so we're allowed to cancel that as much as we want. It's a big help. Now, what do we have left? We've got something where the bottom is going to 1. That's nice. The top is going to 6 plus 0, right? Which we plug in, we just get a 6 here. And that, we really can just plug in, right? Our limit laws say absolutely, we can just plug that in. So this really is just 6. Boom. Cool. That is part of the magic of limit laws and limits. They let you take something that looks kind of nasty and just work it down to something quite simple very often. All right, so we had our polynomial case, we had our dividing by 0 case, and finally let's look at this piecewise function case. All right, I want to know, for this piecewise function, what is the limit as x goes to 0 of f of x? Okay, now this x goes to 0 is at this breakpoint. If it wasn't at the breakpoint, you would just figure out which of these lines has the right domain. But x equals 0 is right when I'm in between these two. And if you're in between two of them, well, I can't just focus on the x cubed or the sine of x. I have to focus on both. So at the breakpoint in those domains, well, one of them is going to have x goes to 0 from the left. One of them is going to have x goes to 0 from the right. So we can say from the left and from the right what is happening. On the left, that means x is going to be less than 0. I'm in this area here, so this would be sine of x. On the right, I'm in x is greater than 0, so I look at x cubed. Okay, I'm going to evaluate these two, and our theorem says that if they agree, there is a limit, and that it'll tell us the value of the limit. If they don't agree, then there isn't a two-sided limit. Okay. So sine of x, I'm going to plug in this 0 into here. At this point, we may or may not have pointed out that we were allowed to plug 0 into sine of x to find this limit. Maybe you looked in a calculator. That's probably okay too right now. But we really are allowed to just plug this in. So this would be sine of 0, which I hope you know without a calculator. Think to yourself, do you know what sine of 0 is without a calculator? You need to know that. It's 0, right? It is the y value when you're at 0 radians. So at 0. On this one from the right, this is a polynomial. I really am allowed to just plug in. So this is 0 cubed, which is just 0. Okay, so the left and right hand limits agree. Okay, which means that this two-sided limit has to be the same as what they agreed to. 0. Ta-da! You didn't have to do this, but just for kicks, if I were to sketch this ever so fast. It looks like on the left, I've got this sine function. On the right, I've got this x cubed function. Okay, and they meet at this beautiful hole right here. All that a limit is ever going to do is fill a hole. Right? It's a fancy mechanism for filling a hole, and it turns out that filling a hole is all you really need to deal with infinitesimals. Pretty neat. Okay, so just to recap, Some functions we can plug in to find their limits. Some functions we have this division by 0, or we're not in their domain and we need to do a bunch of simplification. And then piecewise defined functions are always a little bit of extra work. You need to figure out which domain you're in, and if you are splitting two domains of this piecewise function, then you need to look at the left and the right limits and see if they agree. Okay, that's it. Until next time.